proved by principles of mathematical induction, you're going to follow 3 key steps. Step number 1, you are going to check whether that expression you're given is true for n equals to 1. Then you're going to move to the second step, which we call the assumption step, whereby you assume that if it was true for n equals to 1, then it's going to be true for n equals to k. Then to confirm that that is true, you're going to check if it's true for n equals to n plus 1. If that is true, then it will mean that you can be able to show by mathematical induction that that statement is true. So let me just show you how you're going to follow and different steps you're going to follow in order to score that. Now, in this expression that we are told, it's we want to show that this one is divisible by 4 for all integers, positive integers. Now, we're going to say, we take this expression and we say fn is equals to 3 to n plus 11. So we can say when n equals to 1, let's see how this expression becomes. F of 1 becomes 3, 2 times 1 plus 11, which is going to become what? Which becomes 3 raised to power 2 plus 11, which is equivalent to 9 plus 11, and this is what? This is 20. And this is for n equals to 1. This expression reduced to this, and then 20 can be written as 4 times 5. Now, since this number we are given here can be expressed in the form of 4 times a given number, then it means that this f of n is divisible by 4, because you can see there is a 4 here times a given number, you can get 20. Then we're going to move and say assume this true for n equals to k. Now this is what we call the assumption stage. We're going to assume if it's true for n, well, we're going to say it's true for n. So meaning the formula becomes f of k is equals to, now in this expression, anywhere we have n, we're going to substitute k, and this is going to be 2k, then plus 11. This is the assumption stage. So the next stage now is to check whether it's true. Now we are going to check if it's true for n equals to k plus 1. If it's true for n equals to k plus 1. Now we're going to write this expression in terms of this, so it becomes f of k plus 1 is going to be, the expression is going to be 3 raised to power 2k plus 1, then plus 11. Now let's move together here. Of course, fk plus 1 can be written as, this is 3 raised to power 2k plus 2, then plus 11. This same expression we can be able to say can be written as it can be written as 2k times 3 squared plus 11, because we know that if you are having m power a times m power b, you can be able to say this is the same as m a plus b. So meaning that if you are having this, you can be able to split it. So that's why I'm able to have this. And this means this is going to be 9 here, and we shall say this is 9 into brackets 2k plus 11. So without wasting any time, we can be able to say f of x, not f of x rather, f of k plus 1 is the same as 9 into 3, 2k plus 11. At this point of time, I need to subtract f because already we had gotten our k here, f of k. Just come with me. We had gotten f of k here, and here we have f of k plus 1. So what I want to do, I need to know, is this really divisible by 4? Is it divisible by 4? We have already assumed that this is divisible by 4, and also we check that f of n is divisible by 4 at this point. So our main purpose here is to show that whether this is divisible by 4, right? And to show that, we are going to subtract f of k here and also on this side. So we are going to say this is going to be f of k plus 1 minus f of k is equals to, already we know that this is f of k, so we write it 9, 3, 2k plus 11 minus, here we subtracted f of k, but f of k is what? F of k is this, right? So if we subtracted f of k here, on the other side, what are we going to subtract? We are going to subtract this part. So we are going to say this is going to be 3, 2k plus 11. So we are subtracting that. Now, upon subtracting this, you see we are going to have f of k plus 1 here minus f of k is equals to, if you subtract this and this, you see 11 will cancel out. And if we subtract, this is like having 9 of this, but here we are having just 3 raised to power 2k. So it's like we are having 1 of it. So this minus 1 is going to be equivalent to 8, and that will be into bracket 3, 2k, right? But you see this 8 that we are having here, this 8 that we are having at this point can be written in terms of 4, is a factor of 4. So we can now say the whole of this can go on the other side, and we shall say now f of k plus 1 is equals to f of k, right, plus 4 into 2 of 3, 2k, like that. Yeah. So what I've just done, I've splitted 8 into 2 and what? And 4. So meaning that this term we are having here is a factor of 4. And also this one is a factor of 4. So this means that this one is divisible by 4. This term that we are having here, because we have this 4, so it means is divisible by 4. Also, f of k is divisible by 4, right? Because already we had say assume that it's divisible by what? 4. So this f of k is divisible by 4. This one is also divisible by 4. Then if these two terms are divisible by 4, it also means that this is also divisible by 4. I hope you are getting me. So how will be our proof? How is our conclusion going to be written? How are we going to write our conclusion in this case? We are going to say that now, after you've written this, you must write the conclusion. You must come up with a conclusion for your answer. And this is how we usually structure our conclusion for principle of mathematical induction. We're going to say, since f of n is divisible by 4 when n equals to 1, n equals to k, and n equals to k plus 1 as shown, therefore the expression 3 2n plus 11 is divisible by 4 for all n where n is a member of positive integers. That is how we're going to write our conclusion when we are doing proof by mathematical induction. Right, we have the second question here that says, prove by induction that for all n members of z positive integers where n is greater or equal to 2, in the expression 4 raised to power n plus 6n minus 10 is divisible by 18. We say that the first step is you need to check whether that statement is true for n is greater or equal to 2. So we are going to say this expression that we have can be written f of n is 4 raised to power n plus 6n minus 10. So we say when n is equals to 2, you can just take a number in front of this. We're going to say f of 2 is going to be 4 raised to power 2 plus 6 times 2 minus 10. If you work out this is going to be basically 16, and this 16 plus 12, this will be 16 plus 12 minus 10, this is 10. If we add this is going to translate to 28 minus 10, and you can see this is what? This is 18. So you can see this number 18 that we have here can be written as 18 times 1. So meaning 18 is divisible by 18. So this expression is true. Now, this second step is what we call assumption step. So we're going to say assume true, it's true for n equals to k. Yeah, assume it's true for n equals to k. Then we're going to say the formula becomes what does the formula become? Of course, we're going to say the formula that we are having here become f of k equals to f of k. I'm rewriting this expression with k now. F of k equals to 4 raised to power k plus 6k minus 10. So if it was true for n equals to 2, and we are assuming is true for n equals to k, assumption stage, now we are going to check whether it's true for n equals to k plus 1. So if it's going to be true for n equals to k plus 1, then we will have proven by mathematical induction that this expression is true for all integers, positive integers of z. So check if it's true for n equals to k plus 1. So I'm substituting this into this equation here. We shall have for f k plus 1 equals to 4 raised to k plus 1 plus 6k plus 1 then minus 10. So we can be able, once we have done this, we can be able to say this expression for f of k plus 1 can be written as, we can split this so that we can have 4 raised to power 1 times 4 raised to power k plus this becomes what? Becomes 6k plus 6 minus 10. And finally, we shall have our fk plus 1 reducing to 4 into bracket 4k plus 6k minus, this is actually going to be minus 4. Now, we want to check, is this expression we are having here divisible by 18? To check whether it's divisible by 18, we are going to subtract here. We're going to say this is going to be fk plus 1 minus fk is equals to this part 4 into 4k plus 6k minus 4 subtract, because we are subtracted k here, but f of k. Now we're going to subtract f of k both sides here. So we're going to say f of k plus 1 minus f of k is going to be equals to 4 into 4 power k plus 6k minus 4 minus into bracket, because we subtracted f of k here, but we know f of k is what? F of k is this, this is f of k. So if we subtracted f of k on this part, on the other side, we are going to subtract this expression for f of k also. So we are going to subtract 4 raised to power k plus 6k minus 10. So f of k plus 1 minus f of k is equals to, if we subtract this, we're going to remain with 3 4 power k. Now once I've reached at this given point, I can be able to say my expression will become f of k plus 1 minus f of k is equals to, this is 4 and minus 4 raised to power k, this is 4 raised to power k minus 4, that is going to be 3 4 raised to power k. But this one and this one will cancel out, so this term and this term will cancel out, but this and this one will become now what? Will become minus 4 minus 4 minus minus 10, then we are going to get positive 6 at this given point, right? So there's something I need to do, because I must have an expression to show that this one is divisible by 18. So we shall have f of k plus 1 minus f of k is equals to, I can rewrite this expression that I have here. I can write this expression that I have here as 3 into 4 raised to power k plus 6k minus 10 minus 18 k, then I'll say plus 36. I can see this is not visible, plus 36. So if you can look at this expression that I'm having here, if I open this bracket, 3 times 4k, it will become 3 times 4k, 3 times 4 raised to power k, it will become this expression that we have here. 3 times 6k will become 18k, and 18k minus 18k, we are going to get 0. You don't see k here. And this is 3 times negative 10, it will be negative 30, plus 36, it will be positive 6. So we can be able to return back to this expression that we are having at that point. So whatever that we are having at this point, you can see is representing f of k, right? So meaning that this one is, we can be able to take f of k on the other side, and this part here is representing f of k, because if you can look at this expression that we have here is 4 raised to power k plus 6k minus 10 is exactly what we have here, and we have f of k here. So meaning we can say our f of k plus 1 is equals to f of k plus, but this one we can replace it with f of k, 18 into bracket negative k plus 2, right? So which means that our f of k plus 1 reduces to fk plus 1 reduces to this f of k plus 3 f of k, that becomes 4 f of k plus 18 into 2 minus k. So we need to draw a conclusion for our case here. We need to draw a conclusion for our case. Yeah, we shall say therefore, you can now see, since f of k is divisible by 18, and this term that we're having here is also divisible by 18, then it means that f of k plus 1 is also divisible by 18. Since this is divisible, f of k is divisible by 18 from the assumption stage, and this second term we are having here is also divisible by 18, then it means the entire expression is divisible by 18. So meaning that f of k plus 1 is also divisible by 18. Now we're going to say, now since f of n is equals to 4 raised to power n plus 6n minus 10 is divisible by 18 when n equals to 1, n equals to k, and n equals to k plus 1, as shown here. Therefore, 4 raised to power n plus 6 raised to power 6n minus 10 is divisible by n, all n where n is a member of positive integers. So basically that's what you do in order to prove by mathematical induction that this divisible by 18.